that is head-on overlap of the or head-on overlap of two s orbital or two p orbital, or any hybrid orbital with s or p orbital that gives you sigma 1. Examples of that would be, let me start the, it's easier. Okay, examples of that would be this the S2 hybrid orbital that overlapping, and it gives you sigma bond. You have a s orbital with the hybrid orbital that gives you s orbital. But when you have two p orbitals side by side overlapping, that would give you pi bond. When you do have CC double bond, for CC double bond, there is one sigma bond and one pi bond. For a CC triple bond, it would be one sigma bond and two pi bonds. So if you have two pi bonds, that means two sets of p orbitals would overlap in order to give a pi bond. So if you have sp hybrid, or like for sp hybrid orbitals, you would have like PZ also. So the green color would give you one pi bond and the red one would give you two pi bonds. That's like for alkyne. But for the for alkene, we have only one pi bond here. We have one pi bond and one sigma bond between two carbon. And that would count as the functional group for alkene. So when we are looking at the new family, we want to know about the structure. We want to know about the functional group. We want to, the new terms that is covered in this chapter is called elements of unsaturation. I can move on some of these slides faster because you have the recorded lecture already. I just want to go over the PowerPoint quickly to see if you have any questions. And I am checking the chat. Okay, I will answer your question, Jordan. I just saw that question in the chat area. So if you have any questions, you could or any slide that you want me to spend more time on it, please let me know on in the chat area, and I will stop or I will slow down that. So hybridization for the carbon that carries a double bond is sp2 hybrid. Other carbons of the family could be sp3. It depends on how many sigma and how many pi bonds they have. But for this carbon that carries the carbon that carries the double bond, it's sp2 hybrid. The for a saturated hydrocarbon, you need 2n+2 hydrogen per carbon. Every 2 hydrogen counts for missing 2 hydrogen can count for 1 pi bond. So basically, when you have pi bond, you're satisfying the number of the bonds for the carbon for which is a tetravalent. So you don't have to have, you're missing like 2 hydrogen. So the pi bond every pi bond takes care of 2 hydrogen for this molecule to be proper, like Lewis structure, based on the octet, and the 4 bonds that each carbon needs to have. So general formula for alkene that has 1 double bond is going to be CnH2n. And the other 2 hydrogen is taken care of, but by one of the pi bonds that you have. So for a saturated, you would always compare to this general formula for saturated. And then if we have a molecule that it doesn't follow this formula, it must be unsaturated, or it could be a cyclic compound. It could be a cyclic hydrocarbon. For example, if you have this C8H14, you have to compare that to C8. If you have 8 carbon, is going to be 2 times 8 plus 2, and that would be 18. So 18 hydrogen is needed to saturate this. We are missing 4, and since 4 is missing, and every 2 hydrogen counts for 1 element of unsaturation, it could be 1 pi bond, or a missing 2 hydrogen. These are missing 2 hydrogen. 2 hydrogen can account for 1 pi bond, or it could be like 1 cyclic system. So the structures that can be possible for this molecule is going to be, you have a cyclic system here and a pi bond. So this is a possibility. So we have 2 elements of unsaturation. A two cyclic system is possible. We have 2 cyclic system in the molecule. You have 2 pi bonds in this molecule, so that makes it also possible. You have 2 pi bonds in the molecule A, and that is one of the possible structures for this compound. So being able to count elements of unsaturation, that's one competency for this chapter.
Professor, when figuring that out, we can either use the saturated amount and minus how many hydrogens are in the molecule, or we can just count the elements.
And if your molecule contains halogens, halogen replaces 1 hydrogen. So if you have like a C3H7Cl, how many elements of unsaturation we have for this molecule is going to be, like how many do you need to saturate this molecule? Is C3H8. This is following the CnH2n plus 2. And here you have 3 carbon. There must be like 8 hydrogen. So you have 7 hydrogen and 1 chlorine. That is a 7 plus 1. And this is 0 elements of unsaturation. So there is no elements of unsaturation, no pi bond in this molecule. So if you have halogens, you count as 1 hydrogen. If your molecule contains oxygen, do not count. Just ignore the number of oxygens that you have. And if you have nitrogen, nitrogen counts as 0.5 carbon. So when you're comparing to a saturated molecule, if there are heteroatoms, nitrogen would count as half a carbon, oxygen don't count, and halogens would count as one hydrogen. So elements of unsaturation, and then naming these compounds, the priority is the carbon-carbon double bond. So when you are numbering, you must number from the side that is closer to carbon-carbon double bond. And since the priority is carbon-carbon double bond, you cannot start from here, because if you go straight in this molecule that we are talking about, is going to exclude the carbon-carbon double bond. So you can't start from here. You have to start from the side that it includes the carbon-carbon double bond, and it is closer to that. I'm sure you can get all of this from the recorded PowerPoint that you have. So if there is anything you want me to explain and elaborate on that, let me know. For the, if you have 2 double bonds, so you would number from the side that is going to be, it would give you overall lower number set to the double position of the double bonds. Okay, and when you name it, like if you have 1 double bond, when you name it, when you say like a 2-pentene, you don't have to say 2,3-pentene in this molecule, because carbon-carbon double bond starts with the the number shows that it's you're actually writing the lower number for the carbon, and the other one is understood to be 3. For cycloalkene, so if you have like a cyclohexene, you don't have to even number it because it's understood that it's going to be between carbon 1 and 2. But if you have a methyl group here, then this must be carbon 1 because it has to, you have to give the lowest carbon and then lowest number to the double bond, 2, and then 3. So you just say 3 methyl cyclohexene. You don't have to say 1 cyclohexene because it's understood that for 1 double bond is going to be between carbon 1 and 2. The E and Z designation, it's important for this chapter, being able to classify or name it as a E or Z, and the other term is cis and trans. So please follow these examples. Let me just go to the E and Z designation to make sure that we have the definitions and you know what does it mean. Okay, for a molecule to exist in cis or trans, carbon-carbon double bond must be attached. The carbon that carries the double bond must be attached to 2 different groups. Like this molecule cannot have cis or trans because you have 2 same group attached to this molecule, this carbon in the molecule. This molecule, same, you have 2 hydrogens that are attached, same groups attached to the carbon that carries the double bond, so cannot have cis or trans. When you look at this molecule down here, you have 2 different groups attached to carbon 1 and 2 different groups attached to carbon 2. Now, you can have cis or trans. If the groups are on the same side, obviously they are cis. If they are opposite side, would be trans. When the groups are not exactly the same, so the main part of this slide is that if you have the 2 groups that are the same, they don't exist as cis or trans. The E and Z designation, okay, so same thing here. You do have cis or you have the trans. When you have trans for molecules that they have high electronegativity, if they are on the containing elements with high electronegativity, if they are on the same side, is going to create more dipole moment. The molecule is going to be more polar, but if they are on the opposite side, they would cancel each other's effect of the electronegativity, pulling electrons to opposite side. So when it comes to E and Z, this is the case that you don't have same groups. Like if you had here hydrogen and a CH3, you could just name it as cis or trans. But when the groups attached to the 2 carbons, they are not the same. The term of E and Z is used. So E and Z, you have to give priority to the group attached to the carbon, and you go with the highest atomic mass. So chlorine has higher atomic mass, it would be 1, and of the first element attached to carbon. So CH3 is going to be 2, bromine is going to be 1, and H is going to be 2. High priority, 1, low priority, 2. If high priorities are on the same side, is going to be Z, and if they are on the opposite side, is going to be E. So this molecule would be E, and this molecule, when you have high priorities are on the same side, is going to be Z. If the groups are not exactly the same, how would you determine the priorities? It's like the first element that is attached to carbon double bond. If you have like a tight position, so you have a carbon here and a carbon, so you cannot decide based on these two, then you move a bond away, like further. Is attached to carbon. This one is attached to oxygen. Oxygen takes priority over carbon, so you get the high priority for this group here. And then for these two group, you first look at these carbons. So now is a tight position. Then you move one step away. One step away, you get to chlorine. One step away, you get to carbon. So you just go one step at the time until you get to the point of difference. You don't go further down. So you have your high priority down here. Both priorities, high priorities on the same side is going to give you a Z. When you have carbon-carbon double bond, that means like is attached to two other carbons. So in this case, the carbon is attached to two other carbons, and when you come down here, this carbon is attached to two other hydrogen and one carbon. So that makes the priority going to carbon-carbon double bond. So if you have a double bond over a single bond, double bond takes the priority. Stability of alkene. You get a lot of questions in the exam and the quizzes for stability. Which one is more stable? So basically, when you have a carbon-carbon double bond for a molecule, you have 4 other groups that can be attached. So if you have 4 hydrogen, this basically also can be translated as a 0R. If you have 3 hydrogens attached and 1 R group, 1 carbon and 3 hydrogens, so this is like also, like 1 R. If you have carbon-carbon double bond, that you have 2 R groups and 2 hydrogen, so this is like a 2R. The more R groups attached to the carbon double bond, the more stable the alkene is going to be. So 2R is more stable than 1R, 1R is more stable than the 0R. That makes the difference in these 2 molecules, and this 2 molecule, this counts as based on that definition, there's only 1 alkyl group that is attached and 3 hydrogen to the carbon-carbon double bond. When you look at this molecule down here for the 2-butane, you have 1 group, 2, and 3 groups attached to carbon-carbon double bond. So this is like a 3R. It's going to be more stable than the 1R, the top molecule. If it's more stable, what's going to happen, the more stable it is, or how do they find out that the bottom of this molecule, 2-butene, is more stable than the 1-butene, is because the heat of hydrogenation, the amount of the heat that is being released, is lower. That means this molecule is more stable. The more stable the molecule is, lower the energy that is being released. So when you get examples in different molecules, which one is the most stable, based on the rule is called the SASEP rule. And based on the SASEP rule, we have the stability for the 4R is going to be the most stable alkene. Okay. A trans alkene, they have lower polarity compared to cis alkene. The preparation of alkene, the reactions that is used to prepare alkene is the E1, E2 that was covered in the previous chapter. They are a method for preparation. And also the dehydration, okay? For dehydration, we would use like concept of alcohol, you would use concentrated sulfuric acid or phosphoric acid. For the E1 and E2, when you're looking for a strong base, sometimes you could have like a bulky base. Just be familiar with these three bases or 3 or 4 bases. These bases, they can be used in elimination reaction as a bulky base, okay? And I will show you the difference when the bulky base, if you are using the bulky base, how would that affect the final product? So in the elimination reaction, when leaving group leaves, then base comes in and removes hydrogen. If your molecule has more than one possible hydrogen to be removed, okay? So if you bring like, if you have, in this case, bromine leaving, so you have hydrogen on the right side, the blue color, or hydrogen on the left side, the green color hydrogen to be removed by the base. Depends on the nature of the base. If the base is not a bulky base, is going to remove hydrogen from the position that will give you most stable alkene, and that would be the safe product, okay? So when you say safe product, that means when you have two options, in this case, you get two options. If the blue color is removed, hydrogen is removed by the base, you get these 29% of the product. If the green color is removed, hydrogen is removed, you get 71%. So major product is high. What's the difference between the two? This one is more substituted. So we have one R group here, second R group, and the third R group here. So this molecule basically is a 3R based on my definition that it's not probably very scientific, but you have a 3R alkene. When you look at the other possible structure, you get 1R and 2R, okay? So we have 2R groups. 2R group, this is like most substituted alkene for 3R versus least substituted alkene. So when you have these two choices, which one would be your major product? It depends on the condition of the reaction. Obviously, leaving group has to leave, and then you have to remove a hydrogen. To remove a hydrogen, you need a base. If the base is not bulky, you will get safe product. If the base is bulky, you would get Hoffman product. This product is known as the Hoffman product. So Hoffman product shows you that you have removed hydrogen from least substituted. So why is this effect significant? Because this is too bulky and cannot reach the middle of the molecule, and it would be easier reach for bulky base to come in and remove hydrogen from, whereas not highly substituted. Questions? Removal of the leaving group, leaving base coming in to remove a hydrogen. When it makes a difference, you are going to see that is anti-coplanar. What it means that the base has negative charge or is electron rich, because that's what is looking for hydrogen. And the leaving group takes pair of electrons, so it's going to be negative. So for the base to come in, it's easier to come from opposite side of the molecule. So that is going to yield to a trans molecule, okay? So you would get a trans molecule whenever possible, like you have different groups attached to it. So it's called the anti-coplanar. Which chair conformation is more stable? When you have the bulky group in equatorial position, or if you have the bulky group in the axial position. We learned that in previous chapter, that in chapter 3, that bulky base in equatorial position is more stable, and that's why we have these arrow. The size of the arrow is different, and you get more equilibrium kind of shifts to the left side where you have more stable configuration there. So when we are talking about this anti-coplanar, they must be both in opposite side of the molecule. So if it's opposite side of the molecule in the, then you can get the anti-coplanar. Too many. Here it is. And okay. Questions? So basically, as what we said there, you have to have the removal of the hydrogen is going to happen from anti-coplanar. And when it's if you have like a D-deuterium instead of the hydrogen, see that as a result of elimination reaction, you are getting the deuterium being removed. This is just a proof that this is anti-coplanar removal. So the base is removing the hydrogen from opposite side of the bromine. So when they want to prove the mechanism of the reaction, that's what is like observed. So they say that, okay, if the bromine is going from the up position, because the solid triangle showing the coming toward you, and this is showing that it's going away from you, saying that these two would be removed rather than the bromine and this hydrogen or this hydrogen. So that these two hydrogens, because on the same side of the bromine, they are not being removed. The hydrogen, D is just the hydrogen isotope, is going to be removed from the opposite side. For the elimination reactions, where you have alkyl halide, carbocation intermediate, when it forms, you have a E1 mechanism, and then the base is going to remove the hydrogen, and you have the alkene. When hydrogen is removed, the electrons would drop in, and you get your carbon-carbon double bond. The problem with the E1 mechanism is always like possibility for for the rearrangement. And in the priority is, or the faster reaction, it goes with the tertiary compared to the secondary, compared to the primary. And also, if you are using a base that is not considered the bulky base, your product is going to be safe product, meaning that you get higher substitution of the higher substituted alkene as the product. For the alcohol, you must protonate the OH. OH is not good leaving group, so you must protonate the OH first before it can it can leave. So when you protonate the OH, it changes to H2O. H2O would leave, and the H2O leaves, and you have the carbocation formation. The plus charge would be left behind, so water would leave, and it gives you carbocation. There's a chance for rearrangement whenever possible. Like in this case, there's no benefit for rearrangement and is not going to happen. Another method for preparation, we looked at this before for chapter 3. Actually, we talked about this, is like cracking alkane without providing any hydrogen. It can go through, formation of the alkene. If you add hydrogen, you would get 2 alkane because it's missing 2 hydrogen. It's going to form 1 alkene. This is like industrial method. You don't try this in the lab. Okay. Even though you have 6 carbon in the branch and only 4 carbon in the main carbon chain, because carbon-carbon double bond takes the priority, you have to take this part of the molecule as the main part, and you number it from the side that is closer to carbon-carbon double bond. So it's going to be 1, 2, 3, and 4, and there is a group attached to it. Yes, it's cyclohexane, but when you name it as a branch, it's going to be cyclohexyl, and it's 1-butene because you name this carbon as carbon 1. Did they answer your question? Okay. There was a question about SN1 and SN2 mechanisms or reactions, or the mechanisms. The difference between the SN1 and SN2. Let me see if I can bring the whiteboard here. For the SN1, you have 2-step reaction. For SN2 is 1-step reaction. You have activation energy here, EA. You have transition state here. This is for SN2. Bimolecular nucleophilic substitution reaction. For SN1, you have 1 activation energy, EA1. You get your intermediate, and you get EA2, 2 activation energy. You start with your reactants in both cases. You end up with the products. SN1 reaction, the rate determining step for SN1 reaction involves only substrate. So we have the alkyl halide here. Because it's 2-step reaction, you have 2 EA. The slow step of the reaction is going to determine the rate of the reaction. So only the first part of the reaction is going to affect the rate of the reaction, or the rate is affected only by formation of the carbocation. The second part, because it's fast, that's where carbocation is changing to product. So you have like Rx here, and then here you have R nuc. Okay? Your nucleophile comes in and replaces the X. When the product forms here, this product forming very fast, going from intermediate to product is going to be fast. So fast step doesn't appear in the rate determinants. One rule that you must know like by heart and is very important, the faster the intermediate forms, the faster the reaction. That's one rule. Faster intermediate formation is going to give you faster product. So what type of intermediate works faster, forms faster is the most stable intermediate. So the more stable intermediate is going to give you the major product or faster reaction. Because the intermediate is a tertiary intermediate because the intermediate is a carbocation, then we know that a tertiary carbocation is more stable than secondary carbocation, than primary, than metal. So methyl carbocation. So since tertiary is more stable, it's going to go fastest. That's one of the effects that is going to affect the rate of the reaction, is the nature of the substrate or your alkyl halide. If it's tertiary, it would be faster. Secondary would be slower than tertiary, and so on. The other effect that you have here is the nature of your nucleophile. The nucleophile in SN1 reaction does not have to be very strong nucleophile, because nucleophile comes in on the second step of the reaction. Because it comes in the second step of the reaction, is not involved in the rate determining step, and it's not going to matter if it's strong or if it's weak. So it's going to wait there until carbocation forms. Carbocation is very reactive, and is going to find any nucleophile. It's not going to wait for the strong nucleophile to come and form bond with the carbocation. The solvent, polar protic solvent, is going to promote SN1 reaction, or is going to stabilize the carbocation. When you say polar protic solvent, basically you have in the solvent, you could have ionization, you could have like plus and minus charges. You have a plus charge here that can be stabilized by the negative charge that you get from the, or partially negative charge that you get from your solvent. So polar protic solvent, they favor SN1 reaction. So we are looking for polar protic solvents. Okay. Sometimes they add silver nitrate. Okay. The silver nitrate that they add to reaction mixture to make the reaction go through SN1 reaction. How is going to help? Leaving group is a halide. The leaving group, when it leaves, it can actually form AgX, and AgX is a precipitate. So since AgX is precipitate, it's going to come out of the equilibrium and it's going to make the carbocation to form faster. And the nitrate, because silver nitrate is highly soluble, the nitrate, which is negatively charged, it can stay around the carbocation and is going to stabilize the carbocation. So this is kind of extreme case that how solvent affects the rate of the SN1 reaction. Nitrate is going to stabilize carbocation. Silver is going to remove the halide that was the leaving group and is going to promote the reaction, or is going to make the reaction to go faster. So these are the factors that can affect the SN1 mechanism. What are the problems with the SN1 reaction? Anytime you have formation of carbocation, if the carbocation forms here, there is a chance for rearrangement. The rearrangement is going to happen only when there is a hydrogen on the next carbon, or if there is a methyl group. And why the rearrangement takes place? Because you have a primary carbocation is going to secondary carbocation. If you had a secondary carbocation, this will not rearrange to go to another secondary carbocation. This is not going to happen because there is no benefit there. If you start with primary, you can go to secondary, but from secondary to secondary is not a benefit. If you start from primary and you go to tertiary, that's going to be a lot more favorable, but secondary to tertiary as well, but you never go from secondary to another secondary or secondary to primary. But whenever there is a carbocation formation, there's a possibility for rearrangement. So instead of getting nucleophile attached to carbon 1, your rearranged product is going to be nucleophile attaching to carbon 2. So that's one of the problems with the formation of carbocation. The product of this, the product of a SN1 substitution, in case if this carbon was a chiral carbon, okay, if there was a chiral carbon, because sp2, because of the carbocation is going to have sp2 hybrid, hybridization for carbocation is sp2. That means it has a p orbital that is unhybrid. So the nucleophile can attack from either the top loop, from the up or bottom side of the molecule. And since nucleophile, it has higher priority compared to the carbon and other groups that is already there, because your heavy group or high priority group has left already. That is going to make a difference in the formation of the product. If it's a counterclockwise, it's going to be S. If it's a clockwise, it's going to be R. So we are going to get a mixture of the two products. So you get S and R product, S and R both, okay? Both S and R product. That's about the stereochemistry of the SN1 reaction. Any questions about SN1? So in terms of the configuration, is going to change it can be, you could have either R or S to begin with, but the product is a racemic mixture. So you get mixture of both, because carbocation has an sp2 hybrid and the p orbital that is unhybrid. It allows the nucleophile to form bond from the top or the bottom. Okay, I'm gonna talk about the SN2 now. So for SN2, if I take these out here and just use the space here. For SN2, you have transition state. You don't have carbocation. So basically what is happening in the transition state, your nucleophile is coming in, your leaving group is leaving, and then you have 3 other bonds that is fixed there. That's a transition state. It has very high energy because carbon cannot have more than 4 bonds. When it's tempted to get 5 bonds, it's going to be very shaky and very unstable. So we have SN, in the SN2 type reaction, in the transition state, we have the molecule, a complex that you can see in this complex, the Rx or the substrate is involved, and nucleophile also is involved. And that gives the rate for this reaction being dependent on the Rx as well as the nucleophile. So if you change the concentration of either one of them, the rate of the reaction is going to change. Just because nucleophile is coming in before the leaving group leaves, your nucleophile must be very strong nucleophile. So you need a strong nucleophile. It has to be very brave to attack the carbon while there is something in there, already 4 bonds. So this nucleophile must be very strong nucleophile. And the carbon that you have here, if it's too bulky, is going to hinder the nucleophile. So nucleophile cannot come in to get into the to form bond with the carbocation. So what makes this molecule to be bulky or hindered? It's the presence of the R groups that you have here. You could have hydrogen, or you could have carbon. You could have carbon, like a carbon chain. You could have like cyclic chain or cyclic substitutions, or how bulky it is. The more bulky it is, the slower this reaction, because nucleophile, even though if it's strong, it doesn't have the room to go in there. So you want like the least hindrance for your alkyl halide, and that is going to be provided by a primary. The primary alkyl halide is going to be faster than secondary and faster than tertiary. So okay, and methyl alkyl halide is the fastest, basically. So the degree or the order of your alkyl halide is going to be opposite to the SN1 mechanism. What else we want to know about it is the configuration. You see, it's a back attack. When there is a back attack, the nucleophile comes in from the left side, leaving group is leaving from the right side. So basically, the priority is changing now. If having the X on the left side was clockwise, going from high priority to low priority, when the nucleophile comes in, replaces the X, but is on the left side, is going to change it to opposite. So in this case, actually, R would change to S. S would change. I'm going to change to RX, so we know that this is a R nuc. So S would change to R, and R will change to S. So this is called inversion of the stereo chemistry, or Walden inversion in general, is because that was discovered or proven by Walden. So we have Walden inversion that is happening in the product. So your product would be opposite configuration. One other thing you want to know about the SN2 mechanism, that you do have transition, of course, and the solvent. Your solvents should be polar, but aprotic. Aprotic solvent, like acetone, like dimethyl sulfoxide, like anything that it's polar, but it's not protic, so it doesn't ionize. We don't have any ions forming basically in the transition state. We don't have intermediate, so we need a aprotic solvent for the SN2 mechanism. Okay, Jordan, there was one question and a long answer. Do you have any other questions? Let me look at the other questions. Okay.